Hello and thanks for joining this OpenMP SC23 booth talk. My name is Tom Deakin. I'm a lecturer in Advanced Computer Systems at the University of Bristol in the UK. And I'm going to be talking to you a little bit today about how you can learn how to program GPUs with OpenMP. So these are the things that we'll cover. I'm going to introduce you to this idea that myself and a colleague, Tim Matson, who used to work at Intel, has come up with, called the Common Core of OpenMP for GPU programming. So we'll introduce you to that, and then we're going to go into a little bit of some of the more complex topics about the hierarchy that is there in GPU architectures and how you can exploit that with OpenMP only when you have to break beyond the Common Core. And then finally, I'm going to be sharing some resources and extra places you can look about where you can learn OpenMP, including at supercomputing this year. So here we are. This is the GPU Common Core that me and Tim Matson came up with as we are writing our book, Programming Your GPU with OpenMP. So here it is. It's just this very short list of directives, clauses, and one environment variable from the OpenMP 5.2 specification that you need to program many applications on the GPU. With just the directives here, you're able to get good performance in a lot of cases and make full use of the parallelism on GPUs and deal with the complexities of having a shared a discrete memory space that you can copy data from the host and the device at convenient times that don't slow down your application. So this is the Common Core. This is all you need to program your GPU in OpenMP and get good performance. And this is what we teach in our tutorial too, that we'll be doing at supercomputing this year. And I'll give you some details to that at the end of this short presentation. So over the next few slides, I'm going to be walking through just some of these clauses. And really, this is just to give you a bit of a taster into what it takes to program GPUs with OpenMP. The first of these directives, and arguably the most important, is this one here, Pragma OMP target. Now the target directive is the key thing that differentiates the parts of OpenMP for programming parallel threads in a shared memory system just on the CPU, just on the host, with this idea of having a device attached to that host CPU, and you want to offload and transfer execution from the host to the device and run bits of your program in a completely different place than the place that the application actually started. This idea of heterogeneous programming different types of processors within the same application. So this directive, this compiler directive, Pragma OMP target, really has two roles. It does two things. The first thing it does is it transfers execution from the host to the device. This means your program starts running on the host, and when that thread encounters the target directive, a target task is created and execution is transferred to the device, which then runs the code within the structured block that follows that target directive. Now when that structured block is finished executing on the device, execution is transferred back to the host. Now this is similar in some ways to this the regular OpenMP parallel directive that you see. When that thread encounters the parallel region, then a bunch of threads are created. They go and execute the code that's within that structured block, and when they finished that bit of code, they join up at the end, and execution continues on the original thread. And you can see the parallels here. The host encounters the target directive, a target task is created, and execution is transferred to the device. Now what's interesting here is at this point the host thread stops. It waits for that target task to finish. There are ways to get around this if you need to, using the no-wait directive and all the power in OpenMP for writing task-based algorithms, and all that is available to you through that mechanism. So it is possible, and it comes through the tasking framework that is in OpenMP as well. And it all interacts seamlessly between those two. So the first job of the target directive is to transfer execution to the device. The second is to transfer data to and from the device. So when that target region, that target directive is encountered, for the region defined by that target task, it needs some data, right? The data that lives in the host needs to go over to the device. It might be discrete memory space, it might be shared, but the data needs to be transferred so that it's able to be accessed on that device, on that GPU. Now, there are some implicit rules for this, and these happen every time that target directive is encountered. So things like scalars are mapped first private. This means that every parallel thing that runs on the device gets its own copy of the scalars, but any changes it makes to them are not copied back. But this is really useful. This maps really well to the underlying way GPUs work and how OpenMP is mapped onto those GPU-specific and vendor-specific implementations of parallel programming models. So scalars, they're mapped first private. Everybody gets their own copy of them. Things like stack arrays and structs, where the compiler can figure out how big they are at the beginning of the target task, as that target structure block is encountered, then the data is copied to the device and it's available, a bit like shared memory, into the global memory on the device, available for all the threads on the device to access that single copy that's now in existence on the device, in the device memory space. And at the end, it's copied back to the host, ready to continue using. So these are things like arrays on the stack. So if you allocated a small array of integers or something, that would be copied to, available to be used and updated on the device, and then copied from back again. Now, OpenMP calls this this idea of copying data between the host and the device as mapping, and there are lots of strict rules about how that means, but as we'll see in the next few slides, when we talk about the map clause, how that actually works. So things like stack arrays and complete structs, they are implicitly copied to and from the device at the beginning and end, respectively, of the target task that runs. And finally, what about pointers? Well, pointers are tricky, as we all know when we started to learn C, for instance. But OpenMP has this concept of an array syntax. Now, this is where you can give it a pointer and talk about like a subsection of that array. The implicit behavior of pointers when they're mapped to the device implicitly is this idea of a zero-length array. So it has begins at the beginning and has a no length. So essentially, it's kind of just like a wrap around the pointer value. This means that the pointer can be transferred into the device, and if there is a transformation that needs to happen between the memory spaces, for instance, a host pointer needs to be translated into some device pointer representation. That can all happen there. But again, the runtime is taking care of this automatically for us. The pointer itself is going to be first private if the pointer appears in a map clause. But if it doesn't, then it's just as a zero-length array, and the pointer gets attached to the device that is to the memory that's already been transferred to the device. So what this means for our data then is we can just use those variables with their same original names within that target task. We don't have to rename our variables. We don't have to come up with new device-specific names to say, here's my little array and it lives in the device now. We can just use the same variable name throughout the application on the host and the device. And this implicit behavior and this implicit data transfers will help us move that data around between the potentially discrete memory spaces between the host and the device. So this target compiler directive is very powerful, does those two things. Execution is transferred and will also move some data for us too. So that's it, stage one. We've transferred our data and we've got some programs running on the GPU. But that's not enough. We need to run in parallel. And running in parallel is where the loop directive comes in. Now, the loop directive was a new addition to OpenMP 5. And what it says, if you add it before a loop, like a for loop here, as we do on the slide here, it says that the iterations in that loop are concurrent. That means that they can be run in any order. It doesn't matter what order they run. They can happen, say, in whatever order they like, and perhaps even at the same time. So they could be parallel as well as concurrent. The other thing you do when you use the loop directive is you promise not to use any difficult things to enable that concurrency guarantee to be true inside that loop body. So you're not allowed to make any API calls. That's API calls to the OpenMP runtime. You're not allowed any barriers or anything like that, and there's or almost any other OpenMP directives. There's a very little list of things you can use. Essentially, it's other loop directives and maybe the parallel construct too. But really you're saying here, all iterations of the loop can be run in parallel. Now, the loop construct has some fairly complicated binding rules about which thread they come to share those iterations of the loop across, and whether they share those iterations across those threads or not. But luckily, because of the as-if rule, which is a very common practice within the compiler developers, is you can do whatever you like as long as it maintains the original semantics of the program. So here we're going to take that to our advantage, and compilers can then parallelize this loop across the whole device when the loop directive is used, immediately nested inside a target region. So here, as I said on the previous slide, the target directive brings us to the device, and now with the loop directive, just before the loop, we're saying this is a concurrent loop, and the compiler is free to parallelize that across all of the resources available on our device. So here we are. I've written a big parallel loop, and it runs in parallel on my GPU. And as long as all my data is on the stack, in stack arrays, then everything is fine. I've written a big parallel program that will run successfully on the GPU. But unfortunately, most applications use the heap to allocate the data. They call malloc, that sort of thing. So we need one more piece of the puzzle in order to get our heap allocated data onto the device. Now, I said a little bit about this a couple of slides ago, but in order to get that heap allocated data onto the device, I need to use the map clause. This is a clause that lives with the OpenMP target directives and a few of its friends that all begin target. And this map clause is used to move data where the compiler can't figure out how big it is between the host and device and back again. It's worth just remembering that those implicit rules I introduced a couple of slides ago, they're always in operation. So scalars are always mapped as first private. The stack arrays and the structs of a complete type are mapped same as to from to. But for those things that we don't know how big they are, things like arrays allocated on the heap, for instance, we need to use the map clause in order to generate those data transfers between the host and device and back again. Typically, we do this with our pointer variables. So we list those in the map clause as a list, as we do with all other data sharing clauses. We often have to use this OpenMP array syntax. So here we have our variable name, for example, the pointer a. In that first map clause, we say map2, and then we have the variable a. And we open up with square brackets, and we have these numbers 0, colon, and then an n. Now the OpenMP array syntax is this, as I show on the right of the slide here. We give the start of the array, the offset from the beginning, from that original value a, and the length, the number of, in this case, floats, the number of the data type sized elements that we wish to transfer. Now it's counterintuitive, you might think this is start and end, but it's not. It's start and length, the number of elements you wish to transfer. So here, in the code example, it's just a simple vector add. We have our 3 arrays, A, B, and C. We wish to copy them to the device. Somewhere in our host code, we allocate them. We might have a call to malloc. We may initialize them on the host. And then we get to our target directive. Here we want to transfer and do the vector addition on the GPU. So we write pragma OMP target, and then we have some map clauses. In those map clauses, we specify the direction that we wish the data to be moved between the host and the device. Now, these are always from the perspective of the host. So the host will copy data the 2, for instance, will copy data from the host to the device, and the map from does the other way round. It maps from the device back to the host. So the to and the from is always from the host's perspective, which makes sense, right? It's the host thread that's encountering the target directive along with all of its clauses. So here we are, map to A and B, and it's the full length we're assuming there of n float long. So A and B are copied to the device. So whatever values exist within A and B are made available within that target region to be run on the device. And that's exactly what we need. We take A plus B in the loop, in the penultimate line there. We then have a map from clause. Here we are mapping the updated value of C back to the host. But notice we just specify from. This means that the original value of C is not copied over. And again, this makes sense in the vector addition here that says CI equals AI plus BI. It doesn't matter what the initial value of C is. We don't need to initialize that because it's a write-only operation in our kernel. So with a map from, we copy data at the end of the target region from the device back to the host. We then have our Pragma OMP loop. That's going to allow us to run this vector addition in parallel on the device. So where does our data move? The host encounters the target directive. It copies the A and the B arrays from the host to the device, according to the first map clause. Then the loop construct then tells us to create a whole bunch of threads and use the whole device and share this work in the parallel loop across all threads. So our vector addition is computed in parallel. And finally, the C array is copied from the device back to the host, ready to be used on the host again. So, as I said, those implicit rules are in operation. So the variable n, for instance, if that was a scalar or something, that would be made available on the device to be read in that loop. And those pointers that appear in the map clauses A, B, and C are said to be attached. They appear in a map clause. The data they point to is copied over to the device. And as I said before, we use this same variable A on the host and the device. So when it's inside the target region, we call it an attached pointer. The pointer value itself is translated from the host address space into the device address space. The value is made available inside the kernel as first private, but we can't change it. So it can be quite challenging to do that sort of pointer arithmetic if we need to do that. But we have the pointer value available to us as first private if we want to, but we can't actually update it. We can't change what it points to, for instance. So that's the map clause. We're able to transfer execution, we're able to run in parallel, and we're able to move our data around that's been allocated on the heap as well as the stack. Now the final piece of the puzzle is to keep our data staying on the device for as long as possible and not move it around between the host and the device unnecessarily. This is really important for high performance. Now typically the interconnects between CPUs and GPUs has been much lower bandwidth, much lower performance than the interconnects between the device and the device's own memory. So for example, many GPU systems have a CPU that accesses its own DDR memory and then has a PCIe interconnect to connect it to the GPU, which maybe have high bandwidth memory available on the card. So the GPU to HBM is really fast, CPU to DDR is fast, but CPU to GPU, so transferring from DDR to HBM, is much slower. The bandwidth over PCIe is much more limited. So if we're shuffling data around between the host and the device for every target region that gets encountered, then our performance is going to suffer. So a key for high performance is to keep the data resident on the device. So essentially, put our data in the right place and do all the computation on there for as long as possible before we move it somewhere else. Essentially, the computation is cheap, the moving of the data is expensive. And for that, OpenMP provides us two approaches for this. One is much more structured and one is a bit more unstructured. So the structured approach is the target data directive, Pragma OMP target data. Again, it accepts all those normal map clauses. And what this does is it maps the data from the host into the device as normal. But then for all target regions, so all those structured blocks that follow a Pragma OMP target directive, all that data that was mapped from the preceding target data is already available. We don't need to map it again, and we don't need to specify those map clauses a second time in our code. Essentially, we make the data available in advance. We do all those transfers ahead of time when the target data is encountered, and then when the target regions, the Pragma OMP target inside that are there and available for use, it just inherits that device data environment that was already there. So that's with the structured approach. It can be a bit inconvenient in large code bases to use that structured block way of doing it. We can break those things apart and say when the target data is encountered, we should do something as we enter that region, and when we leave that region, that closing curly brace there, we should do the copying back. So OpenMP gives us these two directives. It's a pair, and they often come in pairs. These are the Pragma OMP target enter data and Pragma OMP target exit data. And they replace the beginning and end of the target data region. Now, this is great. We've mapped our host data onto the device and it's ready for all these target regions. But what if we need to run some code on the host in between those target regions that uses that data? Well, we can't just use those arrays that we mapped without any synchronization. We need to bring them back. But maybe we don't want to end the target data region and destroy everything we set up. To do that, we just need to bring back and synchronize the copies of that data. We have this kind of concept of a mirrored copy between the host and the device, the corresponding variables in OpenMP terminology. So we can use the Pragma OMP target update to synchronize those corresponding copies. This means that we can bring data from the device back to the host, ready to be changed, and then update it on the host and send it back to the device with a second Pragma OMP target update directive. So we have to have that synchronization of data between the host and the device. And there's a little technical reason for that, and that's because OpenMP allows for all this kind of mirage that there is a distinct and separate memory space between the host and the device. It does allow for those to overlap. So we have to make sure that we correctly synchronize. So we can't use the data that we map on the host whilst it's been mapped to the device, but we can update that and make that possible using the target update directive. So that's it. This is the common core. Those are the key things that you need to get programming your GPU with OpenMP. There are some more complexities though that it's worth pointing out. The GPU hardware is hierarchical. So we already see this hierarchy with a host processor with maybe one or more attached devices. But those devices have a hierarchical structure. They're made up of a number of compute units. These are those like symmetric multiprocessors in NVIDIA GPUs. And each of those is made up of these processing elements. Maybe we'd call them CUDA cores for NVIDIA. They very much behave like a vector lane, like a SIMD vector lane. Those are the lanes in each of the individual warps. So we have this hierarchy in our GPU. It's made up of lots of compute units, each of which have lots of processing elements in them. And so far we've learned to express one level of parallelism with the loop directive. It's just one big loop that runs across all of the processing elements in the device. But OpenMP gives us a way to program to this hierarchy. We use this collection of OpenMP compiler directives, the Pragma OMP teams, Pragma OMP distribute, Parallel 4, and occasionally SIMD. The way this works is on this figure on the left-hand side at the bottom of the slide there. So that small arrow coming into the big solid box is our target directive. It encounters it. It starts up the target region on the device. We may then encounter on the device this Pragma OMP teams. We have to encounter it straight away inside the target task. Essentially, we have to write Pragma OMP target teams. And what this does is it creates a bunch of teams, each of which can contain lots of threads. It's a baseball analogy. We create a league of teams. We show this in the dash boxes on the figure. We then have the distribute, and this works a little bit like the work sharing for construct. This shares the work of a loop between teams. Now within a team, everything like it behaves on a CPU, as we know and love with parallel threads in OpenMP, just behaves as normal. We can launch parallel threads and distribute the work between those threads within the team with Pragma OMP parallel and Pragma OMP4 respectively. And we can also use the SIMD clause to say that those threads should be vectorized. What's interesting here is the model of the GPU that I've shown at the top of the slide shows a kind of two-level hierarchy. We have compute units, each of which is made up of multiple processing elements. But OpenMP allows us to express these three levels of hierarchy. We've got a league of teams, each of which can run parallel threads, and each of those threads that's running in parallel in a team could be vectorized with SIMD instructions. Now there are historical regions for this, and for this many compilers now map those teams to the compute units and the parallel threads to the processing elements and ignore the SIMD. But other mappings are possible, and depending on the code you write, you may get different mappings. So it's very important that you profile your code and inspect it and see how it's actually being mapped to the specific GPU with the specific compiler and things that you've chosen for. So with hierarchical parallelism gives you this control, and OpenMP is famous for its spectrum of control of expressing different ideas of concurrency and parallelism. So with this, you get that more control, but it does require more care in order to write portable, performant programs. Now the loop directive, the Pragma OMP loop, has these bind clauses, and with that you can represent much of the same hierarchy while still keeping those restrictions of promising not to use API calls or any other OpenMP directives within the region. Essentially, you still provide those guarantees that the loop iterations can be run concurrently. So that was the Common Core and a glimpse under the hood of where you can build on the Common Core with some of the hierarchical parallelism available in OpenMP that is there to support the fact that the GPU hardware itself is hierarchical. So where can you learn more? The first place is this book here. This book here was written by a number of people very involved in the OpenMP community. It's been around for quite a while. It covers everything in OpenMP 4.5, all the new features. So there's chapters on tasking, which is a very powerful model that was introduced in OpenMP 3. The non-uniform memory access controls that were introduced in OpenMP 4. This gives you an idea of places and where threads should live on the CPU, but also it's got a chapter on GPU programming. So this is a good place to start if you want kind of a general resource for things that were in OpenMP 4.5. But I've been working hard with Tim Matson on this book here, which we're very proud of. This is the Programming Your GPU with OpenMP. This book we wrote, and it covers everything to do with programming GPUs and the target directive and all the things that you need to know in OpenMP 5.2. That's the latest final version of OpenMP. So both of these books, one on the previous slide and this one, they're both available from MIT Press, and there's lots of extra resources for them available online. For this one, ompgpu.com, for example. So if you're interested, do pick this up. It'd be great to share this with you. This book covers all of the Common Core in a lot more detail, but then continues on and covers all of the features in OpenMP 5.2. We talk about the hierarchy that's there in GPU programming. We talk about more complicated data transfers between the host and the device. We talk about how you can interoperate OpenMP with other programming models, things like CUDA and cuBLAS and all those great things that come from your vendor supported libraries. So it's a complete guide to programming GPUs with OpenMP. And if you're able to join us for supercomputing, then there are 4 tutorials that are running during this conference to enable you to learn more about OpenMP. If you've watched this tutorial and made it here and you've never heard of OpenMP before, well, that's fantastic, you've made it this far. But if you'd like to learn some more about the basics, then there's a tutorial happening on Sunday morning that runs all day, which introduces the OpenMP Common Core for CPUs. And that's run by Tim and Helen, Alison and David. Again, on Monday, there's tutorials on tasking, as well as some of the host performance and those 5.2 features that are more advanced. That runs all on Monday with Christian, Michael, Xavier, Bronis, and Rude. And then finally, me and Tim are running a tutorial on Monday on how to program your GPU with OpenMP. So this is a hands-on introduction and covers the Common Core in a lot more detail, along with that hierarchical parallelism. So if you're able to join us for that, you'd be very much welcome. Thank you very much for your time, and I hope you enjoy Supercomputing 2023 and the rest of the OpenMP booth talks.